Okay. So, I'd like everyone to go ahead and have the new assignment. We will be referring to it, looking at various things on it, working some of them together. If you go ahead and grab that so you can see what it is we're doing. Okay. We'll figure it out. So, let's actually put the first couple up on screen now, so everyone can be seeing them together. The first page of the assignment, and a couple questions on the next couple pages as well, are going to be about taking a specific formula and then by hand, and these are straightforward formulas, graphing a few data points to show what that graph would look like. And this is important in physics because these formulas that you see on screen that we'll be graphing are either reminiscent of or are directly based on formulas that we will be using and the types of shapes that those lines will make if we were to look at them expressed over time. The first three are all straight lines. The second three are all parabolas, and I will give you some tips on how to, tips and starting points on making parabolas just a little bit easier because it's a little harder to get them into the space on the page. So I'm going to give you the starting points for those and we'll work on it together. But this is important because in physics, we will be looking very heavily at things called vectors. Has anyone not heard the word vector before? It's okay if you haven't, I just want to know. Okay, at least one. If you haven't used the word vector in math, then you might have at least heard the word first Despicable Me movie, the first villain. And I only bring this up because it's the example I always use because it's just a common point of comparison for everybody. The villain was named Vector because he committed crimes with both direction and magnitude. And then there was something about a squid gun. And that's surprisingly for a kid's movie a very good representation of what a vector is. It is a quantity that possesses magnitude and direction, which is to say it's a line. And so a lot of our formulas in physics and all half of the images and graphs that you will make on the assignment are straight lines because they represent vectors. They always point in a direction and you know where it's headed, what its magnitude is at a specific point in time. So do write this down. This is, sorry, do be taking, I'm a little all over the place today, I apologize. I'll be making these slides available to you, so don't worry about that. But things to remember. There is a difference between a vector quantity and a scalar quantity. A vector has magnitude and direction. Meanwhile, a scalar has only magnitude. when I say magnitude, that is the highfalutin scientist way of saying a number. It has a number that can be measured and stated and calculated. So all numbers that we come across are magnitudes. It is the bigness of whatever we have just measured. Not every number has a direction attached to it, though. Some common examples of vectors. The slide right now lists some things that are common vectors. I'm going to list some numbers with directions to give you an idea of what they might look like in an assignment. First example on the slide is displacement. Something could be displaced 10 miles north. You have to specify what direction you are now displaced in. Velocity. You are speeding up at 16 meters per second in the positive x direction. X, y, and z are directions. This little notation right here tells us along the vector x-axis and in the positive x direction. So on a graph, that would look like an arrow straight to the right. Similarly, you can accelerate in a direction. If you are speeding up, you're accelerating forwards. If you're slowing down, you're accelerating backwards. We'll get more into the fine details of that later. Some things that are always vectors inherently include force, 1,000 newtons up. You can't push on something without pushing in a direction. So in most of our problems, we'll be specifying what direction we're pushing in. Question?
I'm kind of confused on the, oh wait, never mind.
This?
I was going to say the graph, you put an arrow
Oh,
on
yeah, sorry. That graph was for this one. 16 meters per second in the x direction.
and then the 100 newtons up, would that be in the y up?
It would, yes.
Okay.
Oftentimes with vectors, we'll be drawing pictures and putting in little graphs like this to help indicate direction. I will be trying to include as many pictures and visuals as possible, because I'm certainly a visual learner. I suppose I could further specify what direction north is. So every single one needs to have some sort of a direction attached for it to be a vector. And we tend to represent them as lines on graphs. There are some things that can never be vectors. The most famous example is time. Because you can't really have 2 hours east. It's just 2 hours. I suppose you could consider forwards or backwards in time to be a vector, except we don't really have backwards in time. So it's considered a scalar for that reason. We also have mass. Something can have a mass of 55 grams. But mass is just a measure of how much matter is in something. That's not an arrow. Doesn't have a direction. That doesn't change even if your weight changes because you go to a different planet. And temperature is another good one. Can't have 5 degrees up. So we can't graph these. We can't graph a line out of these. We might be able to show change in these things on the graph, but we cannot draw a straight line representing just the concept of 2 hours. So a lot of the work we're going to start doing will involve vectors with directions, and therefore arrows, and occasionally parabolas. And these first 3 things written right here, displacement, velocity, and acceleration, are the first vectors. They're the most basic ones that form the motion of everything in the universe, on Earth and otherwise. So as we begin discussing these quantities more, we're going to start with these formulas, how they relate to each other, how to deal with their vectortude, etc. But to start with, let's begin with what you definitely concretely need to be able to do the assignment. Let's look at these graphs together. I'd like to at least do the first page together, and at least set everything up for you guys. We have all the formulas here. What I'm actually going to do is, I've added a page onto my copy so that I can project this image onto the board, so I don't have to draw a bunch of lines repeatedly. Make technology work for you. On all these graphs, this middlemost point is the origin. We can see the y-axis is defined from -10 to +10. I'm also going to go ahead and specify, because it got cropped off of the image, the x-axis also goes from -10 to +10. So this is a 4-quadrant, fully two-dimensional graph. I don't know why my circle's missing a piece. With that as our origin. And I'm going to put a couple of graphs onto the same one because it's on the screen and I can just manipulate it easier that way without having to erase everything. You have different zones for every single line. But we're going to start. I'm going to try to be using different colors for everything. My red is gone, but I have orange, green, and blue. So number 1 is listed as y is equal to 1.2x plus 2.3. And when graphing things, we can look at, this is defined as the y-intercept, this is defined as the slope. But what is also completely legal is just starting to plug numbers into the formula and seeing what we get back out. For example, the assignment says using at least 4 data points, create your graph. So I'm going to now calculate at least 4 data points. If x was equal to 0, y would be equal to 2.3. So that's our first data point. So on graph, start at origin, 2 and a little more than 2.5. And that is our y-intercept for the first line. Plugging in a 1 is nice and simple, so 1.2 times 1 plus 2.3 is equal to, what we did actually.
2.5.
Thank you very much.
Or 3.5.
3.5, thank you. So we have 3.5. So we start at 1 on the x-axis, scroll up to 3.5. Oh, that's our second data point. Plugging in a 2 is nice and easy. And 5 point what?
5.9.
Thank you. And let's try a -1 as well. That should be 1.2. No, 1.1. So we've got for x equals 2, 1, 2, 3, 4, 5, 9. That's what? That seems a little wrong. Let me check something real quick.
I think it's 4.7.
4.7. I don't know why I wrote down 5.9.
I
I'm sorry.
said.
All right, 4.7. That happens sometimes. Sometimes I mess up my answer keys, and that just becomes a cascading series of errors. And x equals -1 equals 1.1. And that's 4 data points, which pretty comfortably start forming a line. I am going to track down a meter stick, because I forgot to do that this morning. Go ahead and start looking at the next ones. I'll be back in a second. Straight edge. So I don't feel comfortable freehanding really anything. I feel bad at drawing on cell phone. Oh, that's an old door. All right, so in orange, that is line 1. Now, represented as a vector, go ahead and put an arrow on there if you wanted to. This type of formula might represent displacement over time. So I'm going to rewrite this just a little bit. Let's say displacement is a function of 1.2 times time plus 2.3. And this tells us that this person is moving as time elapses. This was the rate of movement of a person. As time is going by, this person will be in a different spot based on how fast they're moving and where they started. So this is, in essence, the displacement formula for moving at a constant velocity. And the other three will look very similar. Something to note about, or the other two, something to note about them is that those formulas are very, very similar. We just switched a few signs around. So formula 2 is y equals 1.2x, sorry, negative 1.2x plus 2.3. Under that one's blue. And 3, I don't know why I'm going in the opposite direction. 3 is y equals negative 1.2x minus 2.3. And looking at these formulas, I can see that number 2 will have the same y-intercept as our first line, because for the both of them, if x equals 0, y will equal 2.1 on both of them. And the third one, since the 2.3 is a negative now, that y-intercept is now down there. I'm just writing them down in coordinate form now, save a little time. Green mark is empty. I think I've made it into that cannon once in my entire time here at the school. So